Okay. Oops. Hello, Professor. My name is Kenny Camara, and today I'll be presenting about Kirchhoff's laws and RLC circuits. Kirchhoff's laws contain a second-order differential equation that allows one to explain and see how an RLC circuit actually works. Kirchhoff's laws are a fundamental principle in electrical circuit theory that is used to describe how electrical currents and voltages behave in a circuit. Kirchhoff's laws contain two parts, the current law and the voltage law. However, we will only be looking at Kirchhoff's voltage law that states that in a closed loop circuit, the sum of voltages must be equal to zero. And on screen, you can see the equation from Kirchhoff's voltage law, where on the left you could see the variables, where R is the resistance from the resistor, L is the inductance from the inductor, C is the capacitance from the capacitor, T is time, I is the current in the circuit, and E is the initial applied voltage, while di over dt is the instant change in the current over time, and d squared I over dt squared is the instant acceleration in current over time. And on the right side, you see the parameters that must be true for the equation to work. You'll see that the initial applied voltage of E must be equal to 0. Otherwise, this will not work. And of course, the resistance, inductance, capacitance, and current must also be greater than 0. I chose this equation to research because I'm interested in computers and electronics. And I have actually heard of Kirchhoff's laws before when I was in a high school robotics class that I very much enjoyed. And when I heard about it again, I really wanted to dig deeper into it because I essentially only knew the name and nothing else about it, which, of course, made me curious and want to research it. Kirchhoff's laws were named after the German physicist Gustav Kirchhoff. Kirchhoff published his laws in 1845 as part of his thesis for his doctorate, showing off both Kirchhoff's current law and voltage law at the same time, where the current law was developed to describe how current flows within a circuit. The voltage law was used to describe the relationship between voltage and current within a circuit. Kirchhoff's laws were mainly developed by Gustav Kirchhoff himself, although they were extended and refined by a myriad of other scientists. One of particular note being Oliver Heaviside, who extended the original equation to include both capacitance and inductance, which is of particular note because we are working with RLC circuits. And other notable contributors are James Clerk Maxwell, who developed Kirchhoff's laws to work with electromagnetic theory, George Simon Ohm, whose work laid a foundation for Kirchhoff's laws, and Leonhard Euler, whose work on complex numbers and differential equations also provided a foundation for Kirchhoff's laws, and of course Sir William Thomson, who extended Kirchhoff's laws to include the effects of temperature and thermal resistance in electrical circuits. Now onto the method of solution. We can clearly see that the equation is a second order differential equation that has constants. So we can use the method of undetermined constants in order to solve, meaning that our first step would of course be to just divide by L. You can see right here that since we of course do know the method, we know that we'll need to get the quadratic formula eventually, so we can take the A, B, and C, which you see in equation number 3, or line number 3. And in line number 4, you see an equation that we will use to substitute with what we got when we divided line number 2, and we will get the equation seen in line number 5. And from there, we will plug that into the quadratic formula and then simply just solve to get the roots. And you can see the process. all the way down. And eventually we will get the roots, where r is equal to negative alpha plus or minus the square root of alpha squared minus omega squared, where alpha is negative r divided by 2l, and omega is the square root of 1 over cl, where alpha is also the damping factor and omega is the resonant frequency. And there are three cases for solutions for these roots, where you could get overdamped, underdamped, and critically damped, all depending on the alpha and omega. You can see the three cases here along with their case solutions. And when a equation is overdamped, it means that the damping force is greater than the resonance of the circuit. So the circuit will oscillate at a slower rate or not at all, which will cause the voltage to decay at an exponential rate to the steady state value. The solutions to the overdamped equations are all unique real roots. For underdamped, it is when the damping force is less than the resonance, which means the entire circuit will oscillate with a certain frequency. The solutions to this are complex roots. For critically damped, it is when the damping force is equal to the resonance, which means the voltage in the circuit will reach a steady state without oscillating, which gives it the theoretical quickest correct voltage, although with the smallest margin for error, making it the least likely to actually happen in a real life scenario. And the solution to critically damped are repeated real roots. And there are some similarities to the equations we learned in class. At the top, you will see Kirchhoff's voltage law, which we just learned. And on the bottom is the simple harmonic equation, which we did talk about in class. And we use it to model springs with the spring constant K and the attached mass of M, where we use the amplitude, constant frequency, and equilibrium point, which is not identical to an RLC circuit's resistor, inductor, and capacitor, which, as you can see, the differential equation for both are essentially the same, which means that the spring system we previously did in class can actually be modeled and simulated using an RLC circuit. As for applications in science, as shown by these graphics, from flipping a light switch to turning on your coffee pot, Kirchhoff's laws and RLC circuits are everywhere in your daily life. They allow the people who designed your home and the engineers to calculate how much energy is needed to properly activate your electronics and technology without causing any adverse effects. And here is a visualization of an RLC circuit where R, the resistor, in a real life example, would be an electronic or piece of technology within the circuit, such as a light bulb or even a phone charger. And moving on, here is a visualization of the types of dampening from over to under to critically damped. You can quite clearly notice that overdamped and critically damped look very, very similar, while the underdamped is wildly different, being a sinusoidal wave function instead. And on to the conclusion. Uh, Kirchhoff's law's differential equations and its relation to RLC circuits can be solved via the method of undetermined coefficients. And solving it will allow us to know the relation between the current and time in the equation. And as a takeaway, although we do not realize it, Kirchhoff's laws and RLC circuits play a vital role in our everyday lives, manifesting in everyday interactions with technology, like turning on a television, and yes, even turning on a light. As for questions I would love to dive deeper into, it would be how would RLC circuits work at larger scales with more components? And how do differing methods of power, alternating current and direct current, affect the circuit's function? Here is my works cited page for the presentation. And here is my works cited page for the paper. Thank you.